I will solve Aerospace Engineering GATE 2020 question number 38. A low-speed uniform flow U0 is incident on an aerofoil of chord C. In the figure, velocity profile from distance downstream of the airfoil is idealized as shown in the section B. The static pressure at section A and B is the same. Drag coefficient of the aerofoil is. So in this problem we have to find what is the drag on this body aerofoil, and at the section A profile uniform flow is there with velocity u0, and at section B we have idealized this velocity profile. At the section A we will assume density as rho infinity, and at section B we will assume it as rho. For solving this question we will use the conservation equation. For conservation equation you can refer to this NPTEL video. We will use the integral form of the conservation equation. Let's say there is this control volume inside the flow, and we will take elementary volume and one surface ds, and velocity from the surface is v, and normal to the surface is ds. For continuity equation can be written as dou by dou t triple integration rho dv plus double integration rho v dot df equal to 0. In this equation, first term represents the rate of increase of mass inside the control volume, and second term represents the outflow of mass from the surface of the control volume. Similarly, we can write the x momentum equation as dou by dou t triple integration rho u dv plus double integration rho u v dot df equal to fx net. This fx net is the net force in the x direction, and this first term represents the change in momentum inside the control volume due to the flow change in flow property, and this second term represents the outflow of the momentum from the control volume from the surface. Now we will start solving the problem. In problem we will use some assumption like we will take the flow as steady flow, and we will neglect all the body force. We have taken one control volume ABCD around this aerofoil. This A, B, C, D are all situated at the infinite, and this x-axis is at the center of this profile. We will assume this density at section A as rho infinity, and density at section B as rho y. Similarly, we will take this velocity at section B as capital Uy for simplicity in solving. First, we will take the continuity equation. As flow is steady, hence this first term will become 0. So equation will become like this. So we will write this equation for all the surfaces of the control volume. For surface A and B, we will first see where is the normal of the surface. Normal of the surface is outward to the control volume, and as we see at AD at section AB and CD, velocity is perpendicular to the normal, hence B dot ds will be 0 for AB and CD section. For section AD, velocity is positive x direction, and for BC is also velocity positive x direction. So dot product will be negative for section AD, and for section BC dot product will be positive. So we will write it as double integration of rho at AD, here density is rho infinity and V is U naught, and ds. Negative sign due to a dot product. Similarly for section BC, it will be rho U ds equal to 0. Now we will simplify it. In the z direction, we will take as a unit length, so our integration will become like integration minus infinity to infinity rho infinity u naught dy plus integration rho minus infinity to infinity rho u dy equal to 0. So it will become integration minus infinity to infinity rho u dy equal to minus infinity to infinity rho infinity u naught dy. We will take this as equation 1. Now we will take x momentum equation. This is the x momentum equation. As we have taken flow as study, hence this first term will become 0. So our equation will become integration, double integration rho u v dot ds equal to fx net. Here let's assume that on the aerofoil this drag force D is acting. So according to Newton's third law, this on the fluid minus D force will act. So net force on the fluid will be minus D minus double integration P I dot ds. This is due to the pressure on the control volume. As we know that pressure at section A and B is same, and the force due to this pressure will become 0. So net force is minus T. So our equation will become double integration rho u v dot ds equal to fx net equal to minus D. Now we will write this double integration in the control volume. So equal to, for double integration there is one dot product v dot ds, and we already have seen that normal of the surface will be outward of the control volume, and at the section AB and CD velocity is perpendicular to the normal, hence dot product will be 0. For section AD velocity and BC velocity in positive x direction, so dot product in AD will be negative due to the opposite direction of normal and velocity, and for BC it will be positive. So we can write for AD it will be rho infinity u naught. This is u naught is due to this u in the equation, and as there is v dot ds also, so there will be also one more u naught and ds. Similarly for BC, rho u square ds. We will take unit length in the z direction, so our integration will become minus infinity to infinity rho infinity u infinity square dy plus rho u square minus infinity to infinity dy equal to 0. Sorry, not 0, equal to d. Equal to minus d. So d will be integration minus infinity to infinity rho infinity square dy minus infinity to infinity rho u square dy. Let's now equation 2. As we have seen in continuity equation, this equation 1, we will multiply both sides by u naught. So our equation will become minus infinity to infinity rho infinity square dy equal to minus infinity to infinity rho u naught dy. So we will substitute this rho infinity u naught square by this term in the momentum equation. So our force d will become integration minus infinity to infinity rho u naught dy minus infinity to infinity rho u square dy. So we will simplify it. So it will become minus infinity to infinity rho u naught minus u dy. As we see that velocity in section B and A is different only from minus cy2 to cy2. Rest is same. This u naught minus u will become 0 for the rest of the length. So it can be written as minus cy2 to cy2 rho u naught minus u dy. Now we will take one assumption. As it is mentioned in the question that flow is at the very low speed, hence density change will be very small, so we will assume that rho is almost equal to rho infinity. Hence our d will become d equal to rho infinity integration minus cy2 to cy2 u naught minus u dy. As in minus cy2 to cy2 u is constant, so all this term will be constant in y direction, so it will become rho infinity u naught minus u integration minus cy2 to cy2 dy, which will become rho naught u c u naught minus u. So coefficient of drag CD will be dy conjugate by 2 rho infinity u naught square c, as we have taken the unit length in z direction, equal to rho infinity u c u naught minus u upon half rho infinity unit square c. It will cancel. So it will become c is equal to 2 u by u naught 1 minus u by u. We put the value of u, so it become 2 into 0.995 into 1 minus 0.995, which will be 2 into 0.995 into 0.005. So it will become 0.00995. We need result till 3 point in the decimal, so it will be 0.010. It will be the answer. This problem is related to the one experiment to finding the drag in using the Wakefire method in any type of body. As we have seen in the solution, we have not used the shape of this aerofoil in finding the drag. So if we have any type of body, we could have still found the drag. And in this question, it is given that pressure is same for section A and B. Even if it were different, we could have solved it. If you wanted to know about more about Wakefire method, you can read about it. Thank you.